Once again, part 3 of Diptarko's series on universalities of non-equilibrium systems. So a couple of announcements. First is Diptarko will give another lecture on the same series. So there will be a fourth lecture, and that will be next week, same time. And the second announcement is that after Diptarko's lecture, we'll have a series by Lata, which starts on June 4th. And that will be on the topic of many-body chaos in quantum mechanics. Okay. So we can start now, Diptarko.
Okay, great. Thank you. Okay, so just to remind ourselves where we stopped last time. So this time I will write a lot of things by hand, so we can go in a regular pace. So you can always stop me and ask me. So from last time, from lecture 2 and part 1, we saw a few things. For example, we encountered the ETH proposal, which was a statement about off-diagonal, it's about these kind of matrix elements in energy eigenstate of local operators. So put an X level for O, delta alpha beta, O E bar. E bar is the average of the energies, plus E power minus S, E bar over 2, some F function, R alpha beta, where this R alpha beta had unit variance. So this was actually from lecture 1, that once these off-diagonal elements are sufficiently suppressed, then we can expect finite energy density states, eigenstates, to approximately behave like thermal states. So as far as measurements go, as far as local measurements go. Then we also saw that we also got introduced to little dynamical questions. So we started asking questions about how the approach to thermalization may take place. And before the correlator, whatever correlator that thermalizes, before the thermalization takes place, there are probes for which there is some notion of quantum chaos, which is captured by growth of unequal time commutators. So of the form phi WTV0 square phi, and we put the square so that there is no phase cancellation. And what appeared here was this kind of out of time ordered correlator with alternating t and 0, t and 0. And this, we argued that this had a behavior 1 minus epsilon over lambda t minus t scrambling. So what is important is this lambda here, which signals the exponential growth of this commutator. And this is called, taking inspiration from classical chaos, this is called the Lyapunov exponent. And then it was natural to ask if there is any relation between ETH and OTOC. And this was answered in this paper by Murthy and Srednicki, which we briefly, not briefly, but we saw through the steps of that paper last time. And that was essentially obtained by inserting complete set of states between the operators. And also here. And then it turned out that one can derive, if this quantity is defined to be, so f of t, one can derive some fall off condition on its Fourier transform, which is f of omega, and it had to behave like e to the power minus 3 omega beta over 4 for large omegas. And there was this kind of a fall off condition also for this function f. This also had a fall off. These fall off conditions were derived by demanding that the asymptotic thermal value is a finite value. Mod x square, this decayed like minus beta mod omega over 4. And then we tried to ask what are the consequences of this in real time. And under some reasonable assumptions, one consequence seemed to be that this lambda gets bounded for thermal state when rho phi, this state rho phi. So I'm writing this as trace rho phi commutator squared. So when this rho phi is rho beta, thermal state, then this lambda is bounded by 2 pi over beta. In general, one expects that the energy scale will play the role of the beta. The ETH temperature will appear. And that is supported in CFT calculations by Sonner and Tadekanos.
Sorry, Diptarko, just so in all these derivations, can you just tell what were the underlying assumptions? I think there were assumptions of like some packing of energy level density is very close to.
Yes. So of course, yes. So so there were a few, there were some underlying assumptions, as Rohan is pointing out. I think, yeah. So that one thing is that the energy levels are behaving almost, the density of states behave almost like a smooth function. That is a assumption, and that necessarily means that we are focusing our attention to really excited states where the spacing between the energy levels become very small, and this is true, for example, in case of CFTs, where we have an exponential growth of the density of states. And this is used because, so if this is our spectrum, here is our ground state, and then we have some states which may be spaced out, but then as we rise in energy, then there are many states which are packed very close to each other. And these are the states which we also expect to thermalize. These are real out of equilibrium states, and for example, ETH is applied to some state sitting in the middle here, which is surrounded by a lot of densely surrounding states, such that this number over here, the suppression is really large. And then, so this is definitely one assumption. Another assumption is about this assumption is tied to the assumption that the uncertainty of energy, if there were many states and we were looking at the matrix element between any of these states nearby, then the uncertainty of the energy had to follow some bound, which we derived in lecture 1 for the ETH approximations to work out. Then these were the general assumptions, main assumptions, which played a role in coming to these criteria. And then there were other further assumptions in trying to understand. Yes.
Excuse me, one question.
Yes.
So this frequency omega, this will be related to this energy gaps, means proportional to this energy gaps.
No, frequency omega is the difference of energy between alpha and beta.
Yeah. Okay. So this separation that you have drawn in this graph, that is also between like different energy levels.
No, here I am talking about when I am looking at. Sorry, when I am looking at, say I am talking about this energy. Say I pick this to be E alpha.
Yeah.
Right, and say I pick this energy to be E beta.
Yes.
Right? So this difference will be omega.
Yeah, that's what I was asking.
Look at
Omega
E
is,
alpha or E beta.
yeah.
That for alpha not equal to beta, this goes like this is exponentially suppressed in omega.
But this suppression means like you said that it's only true when mod omega is tends to infinity, right? The separation is large, then only this follow.
Right. So very good. So you are right, absolutely. So you see here, there is means this suppression will be very small compared to this suppression, because for the cases when omega is small, because this suppression will be the suppression with the average energy, which is excited energy. So this will be extensive in the system size.
Okay.
So the only chance when this suppression may be more than this suppression is when it is some low energy state, when you are looking at some low energy.
Okay.
And then omega is really large.
Oh.
And then that suppression really is meaningful to talk about. Otherwise, we won't even talk about this suppression.
Okay,
but it is very important. It is very important. You have raised a very important point that whatever theory will satisfy such a criteria, a check for that will be if I take this omega too large, it should have the right fall-off condition.
Yeah.
It's a very it's actually a strong test. Okay. So, for example, if you get it from random matrix theory, whatever function you get here, it should have this kind of a follow-off condition.
Okay.
Right. This I will actually, because here this is not relevant. Here what is relevant is the entropic suppression. And if I choose say E alpha prime here and E beta prime somewhere here, then this F alpha, this suppression is more important. Also, you see at lower energies, the spacing between the energy levels will be also more. At higher energies, the spacing will also go down between the energy levels. Okay, so this kind of things are self-consistently built into ETA, and then there is we were talking about the out-of-time order correlator, and here also to have a appreciable range to observe the out-of-time order correlator's growth, we needed this epsilon to be small. Actually, this epsilon is already part of this TS, so I'll remove the T scrambling, because the log of the minus the log of epsilon is related to the scrambling term, 1 over lambda log of 1 over epsilon is the scrambling term. So we need this epsilon parameter to be a small parameter. So that is another underlying thing that is needed from the theory. Okay, and then we also stated that in random matrix theory really provides a way to realize this kind of features in a theory. And random matrix theory arises in cases where the classical theory is chaotic. It shows classical chaos, and then when we quantize it, we get this random matrix theory provides a very good description of that quantum mechanical theory. And a very smoking gun test of RMT is the spectral form factor. Which is basically obtained by looking at the quantity Z beta 1, Z beta 2, which is defined as things are defined in a matrix model. You integrate over all matrices with a distribution. And then you have each of these operators, which is trace e power minus beta 1h, and then trace e power minus beta 2h. And then if you look at beta 1 equals to beta plus it, and beta 2 equals beta minus it, and plot this quantity as a function of time, then initially it decays. Then there is a linear or maybe non-linear also, some kind of rise. And then it plateaus. It plateaus to a value, and usually there are oscillations. Usually there will be oscillations here. There will be oscillations here. And if you average over enough matrices, then for a single realization there will be huge fluctuations. And once you do this matrix averaging, then this will keep smoothing out. And then finally you have this feature where there is a ramp. This is called a ramp. This part is called a ramp. Because usually it is for the simplest matrix models, it is linear. That is why it is called a ramp. Then there is a plateau. And here there is a decay. Okay, and then the occurrence of this is of the square root of the size of the matrix. Occurrence of this is of the size of the matrix. Order. Okay, so these are the things that we saw last time. And then, of course, random matrix theory provides an ideal scenario where these things can be seen and observed. And some of these are also physical and also important for gravity, because random matrix theory also arises in non-perturbative description of string theory. However, we would like to also get to see evidence for these features in more canonical examples of field theories, large N models, conformal theories, and so on. So today's lecture will be assuming that because last time I thought that from the organizers, I got the impression also from you that most of the audience is familiar with conformal theories. So I will provide some evidences from CFTs about some or all of these properties. And there are some other which I have left out, some other properties which I have left out. But however, in CFTs recently, due to development of the program of Bootstrap, these questions have found some answers. There are answers to understanding how these things, each of these things are realized in a CFT and to what extent they are realized. Okay, so that is what I'll do today. And so I'll touch upon each of these, of course, matrix elements. So we also stated last time, we also saw that this in CFTs, this becomes a OPE coefficient because the eigenstates of the Hamiltonian, these alpha and beta, are basically the primaries and the descendants, which characterize irreducible representations of CFTs. And then this is then just a OPE coefficient. And then the question is about the behavior, about the statistics of these OPE coefficients. Okay. And we saw that almost everything is built out of the statistics of OPE coefficient. For example, even this needed a knowledge about higher moments of the OPE coefficients. Because if you remember the derivation from ETH, or basically the derivation of this fall-off condition, that involved looking at higher moment, a fourth moment of the OP coefficient, a specific fourth moment of the OP coefficient. So um, it's important to get the statistics of the OPs correct. And this is a very active area of research currently, and there are calculations, but there are also many conjectures floating around. So one has to be careful when looking at these things, but it's very exciting because it's very active. And then, of course, there's also a goal undertaken to understand spectral form factor, which is different question than either of these, because spectral form factor is sensitive to really late times. Okay, so this ramp and plateau behavior are exponential in entropy scale of time, and therefore they are sensitive to uh, the energy distribution rho E1 E2 when E1 is very close to E2, but different. So they are really sensitive to really the closeness, the discreteness, the closeness as well as the discreteness of the spectrum here. So here in this picture, these are not exactly lying on top of each other. There's a tiny spacing between them, and the spectral form factor is sensitive, responsive to the spacing, the statistics of those spacings. Okay, so that's a different question. And then, of course, I think we ended last time with talking about not just spectral form factor of this kind, but also expecting to see similar features also in more canonical examples like operators separated in time and at finite temperature. And there, if we write it down again in spectral decomposition, then this will look very much like the spectral form factor expression just now. It will be weighted with the OP coefficient square, mod square. So one expects similar features also to hold there, and therein again these matrix elements will also start playing a role in these weighted spectral form factors. Okay, so this is kind of the summary where we stop. Any questions?
What would be spectrum is continuous at after some spacing?
Yes.
Does something qualitatively change in the spectral form factor if the spectrum is continuous?
If the spectrum is continuous, very nice. So if there's so this calculation. So the only place I know where this is calculated is in the random matrix theory, and in also in a CFT example. In both cases, the spectrum is discrete. Because essentially the field theory is on a compact space. So by definition, the spectrum is discrete. Even if you take thermodynamic limit, it only becomes continuous at really infinity. But I suspect that if you really have this to be continuous, then because the spacing will go to zero, you will keep seeing the ramp. It'll keep growing because this time scale is like inversely proportional to this gap between them. So what you expect is that this time scale will be pushed more and more to the right.
Okay.
Okay, but yeah, I don't know what other things will happen for a continuous, because you see the continuous states, like the scattering states, they are not normalizable states usually. So they are not part of the Hilbert space trace.
Yeah.
Right. So they usually in a canonical quantum field theory, those contributions will not be there. But still, you can ask this question. So, for example, if you take one puzzle with ADS3 gravity, or 3D gravity, this problem of Maloney and Witten, one of the problems is that there appears to be non-integral non-integral density of means the Hilbert space trace cannot be written as sum over positive integers. So there it may be there are ways to bypass that problem, but maybe this could what the question you are asking may have some equivalent question in that scenario. Okay, so let's start slowly. So and today it will be mostly it will be review of results in CFTs which sees some or all of these some of these features.
One more question.
Yeah, please.
In this OTU, the commutator square expectation value, what is the one? What is the meaning of that one?
Here, right? This one. Oh, sorry. Yeah, sorry. This is normalized by the disconnected piece.
Okay.
So that
how
that is the dimensionless one.
Physically understand why that disconnected piece dominates at late time?
Disconnected piece dominates because this thing eventually thermalizes, right? Disconnected piece doesn't have any time dependence, so it is the thermal answer.
Okay.
And you can see it also. If you just write down the trace and you demand phase cancellation, then you will see it becomes that disconnected piece.
Okay.
Even here, actually, here what I'm here there is a disconnected piece which gives rise to this plateau. Okay, the connected piece is responsible for this part of this decay and part of this ramp. And what happens actually is that connected piece actually goes to zero after some time, and after that the disconnected piece takes over. Okay, so actually, if I have later, maybe I can show some plots for individually for how the disconnected piece and the connected piece behave. Okay, but this is the full answer, which takes into account both the disconnected as well as the connected piece.
Okay.
Great. Thanks. So, okay, so as we just stated, thermalization question in context of conformal field theories, which is what we will talk about today, will make a very direct contact with the program of conformal bootstrap. And then the questions are, how far are the ETH like ansatz true in context of CFTs? When and how do the exponential entropic separation arise in conformal operator product expansion coefficients? These are the questions. And so we will, of course, we will try to answer this question in two-dimensional CFTs mostly. We'll talk about some things generalized with C greater than 1. And why C greater than 1? Because there's an infinite number of primaries with growing conformal dimension, and you need that because you want to keep the energy density finite in the thermodynamic limit. The energy density goes like conformal dimension over L squared, where L is the circumference of the circle where you put the CFT in. And this you want finite in the limit L going to infinity. So you want a lot of high conformal dimension operators in your spectrum. And that's why it's natural to consider C greater than 1. CFT. Okay, and then the main tool here is basically modular properties in 2D CFTs. And the basic object of study is the torus, CFT on a torus, which is what describes CFT at finite temperature. And first example of a modular bootstrap. So all these techniques go by the name of modular bootstrap. And the first example is the example of the density of states at high energies, which is the Cardi formula. And that starts with CFT on a torus, a finite temperature CFT. And so it has its q variable associated with it, which is e power 2 pi I tau. Tau is the complex modulus of the torus. And for choosing tau to be purely imaginary, this is e power minus beta. So the partition function z of beta, just trace q to the power L0 minus c by 24, q bar L0 bar minus c by 24. This is basically an expansion in this parameter q. Right? So this is basically sum over I e to the power minus beta ei minus c by 12. Okay, and this is what we want to write as an integral, dE rho e, which is the density of states, e to the power minus beta e minus c by 2, where density of states is the usual sum over delta function. And so once we know what z beta is, we can take an inverse Laplace transform to find what is rho of e, which is this formula, which will give us a formula for the density of states. And so the property that comes useful is basically a consequence of the theory being CFT, which is modular invariance, which happens when which is a property which the CFT has once you change the torus. So you change the torus, take tau to minus 1 by tau, and that takes q to q tilde, which is e to the power minus 2 pi I by tau, which is e to the power minus 4 pi square by beta. And under this transformation, you see this parameter. This was a small parameter for large beta. This is a small parameter for small beta. So what used to be a good low temperature expansion parameter has now become a good high temperature expansion parameter. High temperature expansion parameter, e power minus 4 pi square by beta. Okay, so basically at high temperatures, what will be the partition function? So for that, we need the property, how the partition function behaves under the modular transformation. And the answer is that it is invariant under modular transformation. So z of beta equals to z of beta tilde. So this I am defining to be beta tilde. So this means that to get z of beta tilde, I can keep only the first term if I expand in the q tilde variable or in the e power minus beta tilde variable. So this is just going to be, so we know that z of beta is given by this sum. So when beta goes to infinity, this is dominated by e to the power minus beta, and the vacuum has e to be 0. So this is dominated by e to the power plus beta c by 12. This is the leading order term when beta goes to infinity. And so therefore, the leading order term when beta goes to 0 will be given by so this, the high temperature expansion, beta goes to 0, this will be given by e to the power c 4 pi square by beta times 12. So that will be the high temperature answer for the partition function. Okay, is this clear?
Yeah.
Yeah. Okay. Any question? Please ask me now.
So usually when we do the CFT 2-point function and stuff, we do not usually work on a torus, right? Things get complicated if you directly start working on a torus. like to define two
exactly.
point function.
Yeah.
So it's only at the level of partition functions that we are able to work
Yeah,
on.
but to ask these questions about ETH, actually we have to work on the torus. We have to deal with 2-point function on the torus. That is what we will see today later.
And just a naive question, modular invariance of the partition function is simply assumed, is it, from symmetry that it has to be invariant?
Yes. So basically, actually, it turns out that actually it's not guaranteed just from crossing symmetry in genus 0. It is not guaranteed that genus 1 will have this property. So one has to actually show that this is true. It turns out that if you have
even typically one demands modular invariance. Right? Sorry to interrupt. No, I'm sorry to interrupt, but typically one like claims that there should be modular invariance, and then like you this condition one has to put extra, right? That z beta is equals to z beta tilde.
Exactly. So the statement, I think it was I forget the name of Sonada. Yeah. So it was shown by Sonada in 80s that if you want to define consistently a CFT on higher genus Riemann surface, then modular invariance of partition function gives is a necessary condition. So you could have declared that you don't want to study CFT on higher genus Riemann surfaces. Then you don't need modular invariance. Then you could have just worked with the CFT on the plane, and you will be limited to studies of CFT on the plane and of objects which are conformally related to the plane. But if you want to define a CFT on higher genus Riemann surface, then you need to demand modular invariance or some modular properties of CFT.
The reason why I wanted to ask this is because we know that from ADS3 the bulk does not seem to give something which is modular invariant, like the effective action for these gravitons.
Right. So that is true. But the full quantum gravity path integral, not the semi-classical one, will involve a sum over geometries and topologies. So that can give you something modular invariant.
So it is basically this. So it is this. You have to do something like modify the topology and assume that in the path integral these things will be accounted, and the whole thing would be modular invariant.
Yeah, at least you have to sum over boundary topologies.
Okay. But if I'm just locally setting, like, so this is the problem that sort of occurs when we are doing ADS3 CFT2, and if you have like some BTs at black hole.
Yes.
Usually we do not write the 2-point function of the CFT such that it is modular invariant.
Exactly. So this kind of problem was addressed in Maloney and Witten.
Okay.
So they summed over all 3D geometries which give you a torus boundary. Yeah. So that actually involves summing over a family of BTZ saddles, not just the BTZ geometry that we are used to. And that is needed to give you something modular invariant on the boundary.
Okay.
But that has its own problems. That has a problem that finally what you get, the partition function that you get out of that, even though it is modular invariant, it cannot be written as a trace of a unitary theory. So that problem is still not completely solved. So I think this is now being solved a little bit using in at least in the JT gravity context, in the extremal limit, this has some solution in terms of defects and so on. You have to introduce some extra objects.
Okay. Thanks. Yeah.
But very good. So okay. So then you take this answer, which is the high temperature partition function, and then you do an inverse Laplace transform to get rho, and this is the rho that you get. This is the Cardy density of state formula, and what appears here is of course the entropy, because the log of the density of state is the entropy. This you can think also as part of the entropy as some logarithmic correction to the entropy. Actually, this inverse Laplace transform can be done exactly. You get Bessel function, modified Bessel function, and this answer, this twiddle is just representative of E going to infinity limit. Okay, and this is the Cardy entropy, and this has a nice holographic understanding. This corresponds to the area of the BTZ black hole. If you use your radius CFT dictionary, like C equals to 3 LADS over 2G Newton, and you identify R plus with energy and so on, then I will not talk so much about holography, but also this matches. This shows that the black hole area is actually can be interpreted in the dual CFT as some kind of a microstate counting, because this is just the log of the density of state, this area. So this is Cardy's formula, but similar thing will be used to understand basically the OP coefficients. Now we want to do the same thing, not with the partition function, but as Rohan was suggesting, we will look at now the torus with a operator insert, a 1-point function on the torus. So we look at O on the torus. So this is now given by trace O Q L0 minus C by 24 Q bar L0 bar minus C by 24. So again, if I write it in the spectral decomposition, this is going to be sum over I C I O I e to the power minus beta E I minus C by 12. This again I write as an integral dE some function of E to the power minus beta E minus C by 12. This function of E by definition is TOE is by definition equal to sum over I delta E minus EI C E O E. And here I can, if I replace this by average, so then this is, so this, the summation is only sensitive to this delta function. So then this I can write as CEOE times rho of E. So that is that is what TO of E is. And what we want to find out is this TO of E. Just as we had to find out this rho of E. It has the same integral form, Laplace transform. So once we know what is the high temperature approximation of this, we can also do an inverse Laplace transform and find what is this TO of E. So once again, we need to know what is the modular property of this, because now finding this on the torus is a challenging task. But once we know the modular property, we will know what the high temperature behavior of this 1-point function goes like.
Tarko?
Yes, please.
Yeah, I have a maybe basic question about
Yes.
what is the motivation to do such a modular transformation, taking tau to minus 1 over tau.
Yeah.
I mean, minus is there so that we have the right fall-off condition. But what is, just to initial motivation, why is it just something one symmetry one could see, or is there something more?
So yeah, good. So the full modular group is generated by SL2Z, which is tau goes to A tau plus B over C tau plus D. So this is what these are the group of transformations which act on the lattice, on the torus lattice. So if you think of the torus on the 2D lattice with this edge identified with this identified with this, then this is tau, and this side if I take to be 1, then what these transformations do, if these are integers, these just shift the torus, right? So, right, these are just going to change the lattice vectors. What do you mean by the lattice vector? Now, right now, the lattice vectors are this one and this one. If I do this, it will be some different lattice vector. So now this group SL2Z, you can argue that the generators of these are just translations, which are T transformations, which take T tau to tau plus 1, and S transformations, which take tau to minus 1 over tau. Okay. One can show that these two things will generate the full SL2Z.
Okay.
And ABCD are integers with AD minus BC equal to 1. That's the S. That's what S stands for. So, and it turns out that if you interpret this as tau as imaginary beta, I times beta, then it turns out that this, because it takes beta to 1 over beta, it is basically relating high temperature and low temperature. And you can ask, what is the consequence of this? The consequence of this is that I think all the spins have to be even in a unitary theory. And spins are basically differences of holomorphic and anti-holomorphic conformal dimension. They have to be even. So there's a means if you really want to do the full bootstrap, you have to you have to be careful that you don't miss out anything. So there may be some combinations of S and T which may also give you some constraints. So in literature, people have considered also STQ, the action of STQ.
Yeah. Okay. Thanks.
Great. Okay. So again, going back, we will now again, because we are again interested in the high temperature. So we will be again trying to get the high temperature from the low temperature. So again, we will be interested in the S modular transformation, which is this. And this we will do how? This we will basically do because we know what is the, from this decomposition here, we know what is the low temperature expansion of 1-point function. So when beta goes to infinity, we know that this will be dominated by the lowest operator in the spectrum, minus beta e chi minus c by 2. It's some operator which is not the vacuum, because with the vacuum the 1-point function is 0. So it's something above the vacuum such that this OP coefficient is non-zero. Okay, once we know the low temperature answer, and if we know the relationship between O tau and O minus 1 by tau, then we can figure out what is the high temperature approximation to 1-point function. So what is this relationship? There is a very concrete relationship. This is the work of Krauss and Maloney. I should, like I mentioned Cardy here, I should write down Krauss and Maloney. So this O, the relationship between these two O's are basically quite simple. So O of tau bar equals to tau to the power minus h, tau bar to the power minus h bar, O of minus 1 by tau, minus 1 by tau. This happens because under modular transformation, Z, which is the elliptic parameter on the torus, which has the information of where in the torus the operator is inserted, this Z goes to Z over tau. And because these are conformal operators with some weight, when Z goes to Z over tau, these are the conformal factors that you pick up. But once you know this, you can find out what is the high temperature answer. So you can find out using that. You can find that this is equal to 2 pi over beta to the power EO. That comes from these factors. times C chi O chi is there, e to the power minus 4 pi squared by beta, e chi minus C by 2. Now this beta has become 4 pi squared by beta as it happens in modular transformation. And now what you have to do is to take the inverse Laplace transform of this quantity. And that again you can do once you have the inverse Laplace transform, then you know that this t, you have this t, and this t is given by c times rho. So to get c, just divide by rho, and if you do that, this is what you get. This is the average OP coefficient, which is diagonal. E on both sides, O in the middle. So this will be identified with the thermal value. And there is a very nice answer in terms of holography, which also reproduces this, just like the Cardi entropy is reproduced by the area of the PTZ black hole. I'll just show you a picture later. But before that, there are various generalizations of this formula. For example, you can ask, what happens if my symmetry is not just Virasoro, but suppose I have some conserved charge. Okay, suppose I have a U1 charge also conserved in addition to Virasoro. Then it turns out that this property gets modified. This property gets modified. This property gets modified into e to the power minus I pi k mu square by tau plus I k pi mu bar square by tau bar, where this mu and nu bar are like chemical potentials, like call it fugacity. And k is the level of the U1 current. And once again, you can actually use this to again do the bootstrap and find what is now the state has energy as well as charge, some charge Q, O, EQ. And you can find what is the average of this quantity. And this is the answer. You see, basically, wherever you had E, it got replaced by, so delta is same as E. So E got replaced by E minus Q square plus Q bar square over 2K. And interestingly, there is this factor here. This factor has a very interesting interpretation holographically. So firstly, this answer here can be actually obtained from this diagram of this is just a geodesic Witten diagram computation in BTZ. And here what you have is this is the operator dual to O, which comes in, splits into two chi's, and that's because of this factor. There's this factor. This is C chi O chi, this factor, same factor. So this is a vertex which gives results in this phi O splitting to 2 phi chi, and it encircles the horizon. And so you pick up the area of the horizon, and you pick up this length. And if you look at this amplitude from the bulk, it precisely reproduces this factor. And if you want to do the charged case, then it is a charged black hole. There is some charge here, and that creates some field. That creates some field here, field lines. And if you have a charged particle now going around some charged object, so it picks up some Aharonov bomb phase, because the gauge field configuration is non-zero, and you go around. Once you go around it, you pick up some non-trivial Aharonov bomb phase. This is that Aharonov bomb phase. Okay, so there's a very nice story tying these things together. More you will find the references. But I'll not go into much detail, but just to mention that this is, the black hole is a thermal object, and This is just again pointing out that the CFT calculations also have some thermal counterpart in this more exotic setting, C greater than 1 and with a holographic dual.
Sorry, Diptarko, so in the bulk, the computation that you said is done in like one geometry. You're not summing over some different geometry. You're just doing geodesic routing.
That is true. That is true. Because no, here you are doing that because you see, because you are looking at what is essential here is you are looking at high energy. You are looking at EOE, where E is very large, right? Because
Right.
E is very large, the dual is dominated by a very high temperature object, high temperature saddle, and the high temperature saddle is the BTZ saddle.
So it is the high temperature limit of the torus answer which gets mimicked by this thing.
Exactly. That is what also happens if you calculate 2-point function. Only the high, you get the high temperature answer.
Exactly. Yeah. Sure. Yeah.
So it is the same logic here. But if you really want to bootstrap the arbitrary OP coefficient, for that you have to sum over everything. That will be much complicated.
Yeah. So the sum comes in if you're really looking at some finite temperature.
Exactly.
So what is exactly temperature compared to here with the other direction periodicity? Is it?
No. So right. So temperature is actually, you will see what plays the role of temperature. It will be the ETH temperature. It will be the temperature of the black hole. The temperature of the black hole will be given by 2 pi square root 12 times E over C minus 1. Okay, so this is the equation which actually you get if you compare the thermal energy in the BTZ geometry, Hamiltonian, let me write, equal to you demand that this is equal to in the CFT, this in the CFT. So this depends on beta. So you will get that beta. Okay, this is the same thing that you demand in ETH. That you demand that the thermal energy is same as the energy of the state. That this is the equation that you solve to find beta. In this case, you get this to be the beta. So you see here that if E is large, beta is small. Beta small, high temperature. So you so it's a consistent thing all over. That you have high temperature, so BTZ is the right thing to consider.
Okay, thanks.
But of course, one will like to do better. Maybe it will be interesting to repeat the same calculation, but now using this Maloney-Witten prescription of summing over these different kinds of filling up the torus and see what one gets. That will be interesting thing to do. Okay, so this is giving information about OP coefficient of this kind, heavy, fixed, O is fixed and heavy. So we get information about this kind. Now there are now one can use the conventional bootstrap as well, which is represented by this diagram. This is on the plane. Now this is on the plane. So we were talking about the torus till now. Now back to the plane. On plane we have the crossing equation. This is the crossing equation on the plane, and from here actually also one can get some constraints on OP coefficients. Basically, there is a very useful mapping which maps this plane. It cannot, of course, a plane cannot be mapped to a torus by conformal transformations, but it can be mapped to something called a pilogeometry, which is like a torus mod Z2. And in that geometry, there is a notion of a temperature and so on. And that can be used. And there is a notion of a modular transformation again in that geometry. So you start from the plane Z, but you go to this pillow geometry, looks like a pillow, and here there is some notion of a modular parameter tau. And therefore there is a notion of a S transformation. And what is interesting, very interesting, is the crossing equation, which is basically the equality of this correlator under Z goes to 1 minus Z. This crossing equation becomes the S transform in this geometry, in the pillow geometry. And one can again use that to one's advantage, like Krauss-Maloney had done. And what one gets is actually the OP coefficient where two of them are fixed and one of them is taken to infinity. So it's like light and heavy, light and heavy, and even here you have this suppression. You have this entropic suppression, and this, if you look into the holographic dual, it really corresponds to this amplitude, where in the middle channel you have a black. You have a very massive object, and because of this black hole, so this is a process. This is a process which is the amplitude of two light particles coming in, forming a black hole, and then that black hole decaying back to the two light particles. Okay, and this is exactly the same two light particles, and this is an extremely suppressed thing. Formation of the black hole happens at a. So if you just ask the question, what is the probability that two light particles of sufficient energy will form a black hole? That has very high probability. But now you are asking that what is the probability that it forms a black hole and then it decays back to the same light particles? That has a very suppressed probability, and this amplitude has this entropic suppression, e power minus ft by.
Sorry, in what limit does this process terminate?
Yeah, this process is dominating. This process. Very good. So are you asking what is the so this will be a function of cross ratio? Are you asking which channel in the cross ratio?
No. I'm asking a simpler thing. What did you do to say that the heavy operator is dominant? You took some limit. I sort of forgot.
Yeah. So great. So what I did is, so in terms of Z, it is difficult to see this limit. In terms of Q, it is again this high temperature, low temperature limit. But Q is related to Z very non-trivially by these equations. So in terms of Z, it is some very weird limit in terms of the cross ratio. So here you see the setup is just 4-point function on the plane, and this I am mapping to the pillow geometry. There is no torus here, but that pillow geometry has its own modular parameter and notion of a S transformation.
So it has a notion of a temperature akin to a torus.
It has a notion of temperature, so it is in that temperature. It is like a high temperature limit.
Okay.
Yeah, but you can frame it as some limit in terms of the cross ratio. You have to place your operators in some very
specific points. Yeah.
Points exactly. Then you can get that. So good. Okay. So then Then of course you can try to ask the real question of ETH, which is the off diagonal OP coefficient, which is C E O E prime, right? And this kind of a OP coefficient, because this is really the off diagonal OP coefficient that enters into ETH, and this can be answered by looking into this 2-point function on the torus. 2-point function of O on the torus, and there are two channels, the S channel and the T channel, and this corresponds to the S channel, on the torus with 2 operator insertions. And this again, if you write in spectral decomposition, this will have dE, d omega, some TO or J O E omega, e to the power IT omega, where omega is the difference between E and E prime, and E is the sum of E and E prime by 2. So the average of E and E prime. And this J of O now has information about, so this is sum over Ij C EI O Ej mod square. This has the information about the off-diagonal OP coefficient. So once again, if we manage to find what is the high temperature approximation of this, then we can find what is the high energy approximation. So high energy meaning both E and E prime are now large, and what is the approximation of this OP coefficient. Okay, and this one can just follow the steps and do the same thing by again using the modular property on the torus, and this is the answer that one gets. Okay, now here I want you to notice these 2 things. One is that this entropic suppression is there for this for the off-diagonal case. This is the correct entropic suppression. And the function of omega, you remember from the discussion of ETH, we had for alpha not equal to beta, we had a e power minus, for mod square, we had e power minus s, which is this factor. And then there was this factor e omega mod square, which is this factor. So we can identify these 2 factors. And if you look at what is the large omega fall-off condition of this, indeed, you will see, if you expand the gamma functions, you will see that this indeed has the correct fall-off condition. This goes like e to the power minus beta mod omega by 4, where beta is the ETH beta, where beta is 2 pi over 12 delta average C. Okay, so these features are indeed there in this large CCFT for very excited states, which one gets from modular bootstrap. So both these features, this fall-off as well as this entropic suppression, which is very important. Okay, and here again, there is a very nice holographic interpretation of this result. Here you see what is this amplitude? What is this amplitude going to be? This amplitude, each of these heavy states are like black hole states. This is like a black hole, very heavy black hole, which is being disturbed by some operator, and it settles down to some other black hole. So it's like there is a black hole state, which is this delta prime. It goes to delta by interacting with some operator. And this kind of calculation in semi-classical gravity is the calculation that one does to investigate quasi-normal modes. And one gets this absorption and this emission cross sections, and one actually reproduces this factor. This is the factor which appears in the GR in covered space-time calculations. Okay. So this is exactly that factor. This is just a probabilistic factor for this process to take place, and this is the gray body, or this is this emission or absorption factor, which and this kind of a scenario that this kind of a thing can also happen from a CFT calculation. This was already pointed out by Maldacena and Strominger in this universal low energy dynamics paper on black holes. So it's a very nice paper, and this section about 2D CFTs is very reminiscent of this kind of a calculation. Even though that was, I think, in 2010 probably, or maybe earlier. Okay, so this was what I wanted to say about these bootstrap results. Now, little bit I want to talk about, I'll take maybe 10 minutes. Is that okay? 10, 15 minutes?
Yeah, sure.
Yeah. Okay. This is again, this is about subsystem ETH. Remember when we were discussing ETH, we also talked about what will happen if the probe is not local. If the probe has a finite support, then we decided that what we should compare are the reduced density matrices. We should compare rho psi of some subregion A, and we should compare this with rho beta of the same subregion A. And this is again taken from this paper by Tarun Grover and Jim Garrison. And here they have done this comparison for this non-integrable Ising model. And what they plot here is the trace distance between trace A, rho psi A minus rho beta A to the power some P. I think P is for them some integer or a half integer. This basically, this denotes a trace distance. And they plot it for different subsystem sizes. So each of these colors, so each of these plots are for different subsystem sizes. You see here, this blue color here, this blue color is when the subsystem size is 5 and the total system size is changing. Okay, so this distance is when the subsystem over the total system size is 1/4. This is here, it's when it's 1/3. So you see, when the subsystem size divided by the total size is increasing, the trace distance is also increasing. Right? But interestingly, it seems to follow some kind of a power law growth. So what this seems to behave like LA over L to the power some number. Okay, and whenever you see this kind of a feature, it is natural to try to ask whether you can see, whether you can talk about some universality of this exponent by doing this calculation in a CFT. Okay, so that is what you can try to do. And the simplest calculation in a CFT is when this is 2, because when this is 2, when this is 2, when this is 2, this object is just trace A rho psi A square plus trace A rho beta A square plus twice trace A rho beta A rho psi trace. So that's why I use the cyclic property of the trace to write 2 times. And so this is what you have to calculate in the CFT. And this is the object which is just the second Renyi entropy of the excited state psi. This is the second thermal Renyi entropy, and this is a strange object. This involves gluing the torus to a cylinder. So this is what you have to calculate, and this there are many ways to do this. One easy and convenient way is to use the cutting and sewing method. This good reference is Polchinski's chapter 9.
Just one small thing.
Yes.
In this equation, it will be minus in front of 2 traces.
Oh, sorry, you are right. Yeah, of course. So this, but now you have to calculate each of these objects. So, this I will not describe. You can take a look at our paper. But essentially, what this boils down to is replacing this tube by a sum over insertions. So you get rid of this tube and you insert complete set of states and you sum over all the possible insertions. So that takes care of propagation here. There is also a very nice review by Ashok Sen, a CFT review from 90s. It's in Pramana. It's called higher genus CFT, something like higher genus CFT. CFT is on higher genus Riemann surface.
So here beta is determined how? By looking at which energy?
Yeah, exactly. Sorry, yeah, I should have said beta. Beta is determined using the equation, the same equation. You look at psi t psi. This you calculate using word identity. Set this equal to trace t e power minus beta, and you solve for beta. In the high temperature regime, this again becomes just this becomes proportional to 1 by beta square, right? So then you can solve for beta, and you get beta to be equal to 2 pi 12 delta psi by c minus 1.
Thanks.
Yeah. Okay. So you can, of course, it's interesting. You can ask what happens if I take. So this is again high temperature approximation. You can ask what happens if I take the corrections. These corrections will be exponentially suppressed. These corrections will be e to the power minus 4 pi squared by beta times some numbers. So what happens if you take into account these corrections, how this will change and how will this change? So this kind of questions one can ask. But the effect will be very small. Okay, so one can do this calculation, and then what one gets for this trace distance is sum over k1 k2 c k1 k2 times some like this displacement delta, where delta xk is psi ok psi minus ok. So this is what one gets out of this, and then this form of the answer, and then you calculate some leading order terms in this expansion that reproduces this power law behavior, and it predicts what will be the slope of this and so on. So this is again a feature of ETH, subsystem ETH, the trace distance, which one can get some indication of this from the CFT. Okay, so this was about ETH and about some discussion about thermalization and evidence for this through the bootstrap program in 2D CFTs. And you can see here already that another interesting feature that so for being thermal, this has to go to 0. If this is a primary operator, at high temperatures, the 1-point function goes to 0 automatically. And this is just the OP coefficient. This is the OP coefficient. And this is given by, we know this is already given by the Krauss-Maloney formula. So now here, the exponential suppression of the OP coefficient plays a role. You see that because these OP coefficients are exponentially suppressed, this is small. The distance is small. So it directly feeds into the properties that we bootstrap using modular properties, which played a role in this local ETH, directly is now feeding into this minimizing this trace disk. Okay, so this is another evidence for, not evidence, another investigation in context of CFTs of thermalization and so on. Okay, now next a little bit, I just want to, this I will not do at all in detail. I'll just point out some references. There has been a lot of study about out of time ordered correlators also in CFTs. Time ordered correlators in CFTs, and I'll end today with this, and then next time we will talk about a little bit about spectral form factors and quenches, finally about quenches. So out of time ordered correlators in CFTs is again basically is the basic object that we want to calculate. We want to calculate VT W0, VT W0, maybe in a thermal state. Okay, and the way this calculation proceeds is first to realize what does it mean to calculate out of time ordered correlator, and that boils down to understanding time ordering of correlators in quantum field theory. So time ordering is one way to talk about time ordering, or to talk about Lorentzian correlators, especially relevant, and this is especially relevant for CFTs, is to start with the Euclidean correlator and do analytic continuation. So what we do, so because we are, every time we are quantizing, we were studying a CFT, we are quantizing our theory in radial quantization, so we are always in a Euclidean picture. The Hilbert space is obtained by doing radial quantization. So all our calculations are done in the Euclidean setting. And then when we ask Lorentzian questions, like questions of dynamics, like this question, then we need to do analytic continuation to real time. So we start with the Euclidean correlator, which is a function of tau. Tau is the Euclidean time. Euclidean time. And then we do analytic continuation to IT. This is the Lorentzian. Now, the fact is that this is an ambiguous step. Okay, it is both good and bad. Probably more good because one can use this ambiguity to generate different orderings, time orderings. So just consider for the moment a 2-point function in Euclidean. Okay, and if you look at where are the singularities, so there will be some singularities in the complex tau plane. In the complex tau plane, there will be some singularities of this object, So this will be some Euclidean object, and then you can ask what is the complex structure in the complex tau plane? What is the analytic structure of this object? And can anyone tell me where, for a CFT, suppose for a CFT, where will be the singularities of this object in the complex tau plane?
So when the operators approach each other, right? So it will be
exactly. But on the basically on the light cone. So because so in the complex tau plane, this will be when tau is basically IX. When tau is IX, there will be some branch cut singularity. But there will be also one at minus IX. Okay, so there will be some singularities, and now what we want to do to calculate the Lorentzian correlator, we calculate first the Euclidean correlator, which is tau is some real value, and then we have to analytically continue. If we analytically continue here, at this time, at this value of time, say t1, this value of time which doesn't cross, which doesn't see this singularity, that means the 2 points are still space-like separated from each other. Because it is here, that means basically t1 square minus x square is positive. Sorry, space-like is negative, because you see x, this is x, the distance x is larger than t1. So this is negative and this doesn't see, and this object is 0. But now when they are space-like, which means it crosses this and then it will see this singularity, then there's an ambiguity, because there's a branch cut. The complex plane here is different from the complex plane here, in the sense that this function may be multi-valued across the branch cut. There may be a discontinuity. So then for this case, there are clearly two choices. One is reaching this point, this time-like point. This is a time-like point, time-like separation, either from here or from the other way, other direction. There are these two ways, and the convention is one of them you choose to give time ordered correlated, the other you get the anti-time ordered correlated. And whenever, so basically the way these two contours differ by A and B, if you look at the difference of A and B, it's basically the commutator between OTX and O1TX and O2C. So, and because it is commutator, if one gives you time ordered, the other will give you anti-time. So the convention is, if you go via the right side of the singularity, you get time ordered. If you go via the left side, you get anti-time. Okay. Here the setting is complicated, a little more complicated, because it involves more operators. So this is homework. So now the setting is, there's one operator here. So by using conformal symmetry, I can set 3 of them to be at 0, 1, and infinity, and the other one will depend on the cross ratio, which I will later analytically continue. And I will analytically continue in such a way so as to reproduce this time order. So this is O1, which is at 0. There is some O3, which is at 1, and another one I will send to infinity, O4. Will not worry about that. The light cones will be too far away to do anything. And let's draw the light cones. And let's consider this operator O2 here. And let's look at the analytic structure now in the complex tau2 plane. Tau2 is basically this. Let this axis be y, this axis be tau, this axis be t. Okay. And tau2 is the complexified time coordinate of the operator O2. So where are the branch cuts now? So now there will be a branch cut. So if as long as it is here, it is space-like separated from all the operators, O1, O3, O4. So then there's no problem here to do analytic continuation. I can always do some analytic continuation. But first, let's draw the position of the branch cut. So one will be at I y2 minus y1. That is when this crosses the light cone of 1. There will be this branch cut. There will be a similar structure here. Okay. And then there will be a branch cut at I y3 minus y2. y3 is maybe 1 or something. It will be here. Now, if I want to do analytic continuations, if I continue to here, there's no problem. It's still space-like. That's some point here. But now, say I want to analytically continue here, which is somewhere in between these two operators. So I can go this way, or I can go this way. It will either be time ordered with respect to this operator or anti-time ordered with respect to that operator. But what we want finally is to reach some point here. We want to reach some point here. To reach some point here, if you look at the expression, we want to reach here. And we want O2 to be time ordered with respect to O1, but not time ordered with respect to O3. We don't want, this is O2, we want it to be time ordered with respect to O1, but not time ordered with respect to O3. So then the way we will go about doing that is we will go to the right of this, but then we will turn and go reach here, not there, reach here. If we for example, if we took this purple route to reach 204, this would have given us a time ordered correlation function. This would have given us O3, O2, O3, O1, O4. This is time ordered. This is that point finally that we are reaching. But if we follow this blue route, if we follow the blue route, then we get basically we get O4 is here. O2 is time ordered with respect to O1, no problem. But O2 and O3 are not time ordered with respect to each other. We get O3, O2. We get O3, O2, O1, O4. And this is the combination that we need. Okay, and this one, if we look at what happens in the complex plane with the complexified Euclidean, with the Euclidean correlator, this corresponds to taking Z around the point 1. So take Z around point 1. Point 1 is the location of O3 because it is not time ordered with respect to O3. And that corresponds to taking Z minus 1 to Z minus 1 e to the power 2 pi. So that's like going around the point 1. And so this is the operation that you have to do to the Euclidean correlator, and this is what will finally give you the answer with some subtleties which we'll mention next time. We'll get lambda equal to 2 pi by beta if you do it for a thermal state. Okay, so this is where I will stop today because spent a lot of time. Sorry for being slow, but I wanted to cover all these results to give you an overview about where, from the line of CFTs, where we stand with these questions. There has been more developments which I have not covered today. There have been more bootstrap results. Also, there have been thermal bootstrap in higher dimensions, which I've just skipped. But this, you will now have an idea of what kind of questions are still to be answered, or what people are thinking about. Okay, so I'll stop here today. Next time I will talk a little bit about spectral form factor, and I will go directly into quenches.
Okay, thanks Diptarko for that lecture. Now let's take questions.
Please.
Just to summarize, you first showed that if you assume modular invariance in CFT, you are able to solve for the partition function and 1.5 function of an operator at given the low temperature answer, you can get the high temperature answer.
Yes.
Just by modular invariance, and then you can test what are these precise functions that appear in the ETH hypothesis. That is the right thing, right?
Yes. Yes.
I think yeah. So sorry. Go ahead.
No. Please. Yeah.
Yeah, so here you never. So you might cover this next time, but here you never assumed that the CFT is an ensemble of CFT or something. So these features are sort of there always.
Yeah, these features are definitely there.
Yeah.
These features did not require exactly. This is very excellent. So yeah, these didn't require any ensemble to be there, but for the spectral form factor, it will actually require some to reproduce that from the CFT. It will require a presence of an ensemble.
Exactly. But even this ensemble, just daydreaming out in the since it's there, it could be thought of as some large CFT, where you have some at some kind of a like I'm thinking in the lines of tensor SYK model, which mimics the ensemble of SYK models at large N. So, but the tensor SYK model is unitary, but it simply means that the tensor SYK model is a bit more complicated with gauge, with all these gauge bosons and everything, gauge boson interaction and stuff, such that effectively it is mimicked by an ensemble of CFTs like the non-tensor SYK model. So
that is very interesting. Even if someone can find one example. CFT example in some 2D CFT example where one can get this kind of a ramp and plateau kind of feature without doing ensemble average. That will be very interesting.
But we know this even from like from string theory, right? We know like there is no ensemble of CFTs. It's just like some.
That is true, but there we don't know any calculation of the spectral form factor.
Exactly. So CFT is so complicated, or whatever is the the CFT is so complicated that we can't.
So no, there is one solvable example, which is this free orbifold point in ADS3 cross this T2, which was actually computed by this Lorenz Eberhard. And there you don't find any spectral form factor growth. You don't find OTOC like behavior also.
Oh Lord, okay.
Yeah.
But this ensemble business has to be clearly if string theory and everything, this is a unitary thing. Ensemble has to be an effective description of some kind of a field theory which is unitary. Ensemble of CFTs. It cannot simply, I mean, we cannot certainly be talking about in the middle of doing string theory, certainly be talking about some ensembles of CFTs.
That is true. But as far as to, one can take the viewpoint that to explain these kind of phenomena, one may just to do computations like that. One can use the ensemble picture.
Yes. So so to if you want to explain interesting physics in the bulk by doing semi-classical gravity, then the good way to look at it is an ensemble of CFTs.
Yes.
But I mean, just to get my head around the fact that I mean, all the time we were talking that holography and string theory has solved the page curve just by the statement that holography and string theory exist and there are black hole solutions and it's all unitary. But now we cannot come to explaining like gravity is like an ensemble of CFTs. Right? It's only an effective description.
Yeah, exactly. So and also there means even within a unitary CFT there may be some ways to generate this ensemble effect.
Yeah.
So that means, and I think there's not much done in this direction. How to generate ensemble within a CFT, within a particular theory. So one idea which is from this, which is from the this second lecture, is again this thing which was pointed out by Liu and Grover, if you remember, was this finding the subregion A and A bar, and then writing the state in terms of eigenstates of A and eigenstate of A bar.
Oh, okay.
And then this turned out to be a random matrix, the Cij. So this will be a calculation within a CFT. Within a CFT, if one can find the eigenstates of the Hamiltonian acting only on A and A bar. But that is a difficult calculation to do.
Mm-hmm. Okay.
So things like this. Also there is another thing where RMT appears, where if you look at EI, OT, O0, EJ, you view this as a matrix in IJ index.
Yes.
And then there is a statement that this, as a function of IJ index, this is supposed to be like a random matrix. So in these cases, the ensemble is provided by different eigenstates of the same unitary field. Kind of.
So there are features of RMT which are sort of visible in obviously unitary CFT. I mean, in a single CFT, not an ensemble of CFT. But this plateau ramp thing, which is sort of like this thing of wormholes and everything. Yeah. That if you can show sitting in just like one CFT, then that would be something really good.
Yeah. So that is, I think that is the question. Easy to answer. Yeah. Otherwise, RMT or ensemble like features are already there.
Yeah. That you anyways.
Exactly.
Sure.
That is how you started the question. Yes.
Yeah. Sure. Yes. Thanks a lot. Thanks.
Yeah.
In that graph that you drawn showed the 1 over L. Yeah, this graph. So this L values, what this again?
Yeah, sorry. L is the total system size. Okay, of the spin chain over which the simulation was done, and LA is the size of the subsystem over which the reduced density matrix was calculated.
So it's like when you are dividing like in A and A complement, LA is
LA is 5 and A complement is 15, for example, for this part.
Okay.
Yes, this is a 1D spin chain. This figure is taken from I didn't write. So this figure is taken from Garrison and Grover. Grover 2015. Yeah, this is a really nice paper. So everyone can take a look.
Any other questions? Okay, since there are no other questions, thanks Diptaku again for the very nice lecture, and we'll see you again next week.
Yeah, see you next week. Okay, bye.